Hello, in this video, I'm going to be telling you about forces and free body diagrams. In class, we've been discussing why different objects move in the way they do. You've made observations about how large objects end up moving much more slowly. They resist changing their speed, a lot more so than small objects, which can accelerate really fast. If we really want to understand why smaller objects and bigger objects move in the way they do, we can understand forces and free body diagrams to help us explain what's going on. So a free body diagram is a picture. It's a diagram that shows all of the forces acting on one object, all of the forces that are pushing or pulling on that one object. And it helps us to understand if the object will accelerate or if the opposing forces on an object will cancel each other out. So before we get into it, I have a question for you. I'd like you to think about this. I weigh about 78.6 kilograms. That's about 173 pounds. And I weighed myself. I stood on a scale and I weighed myself and it said 78.6 kilograms. And I wondered if I took that scale and I put it on a ramp and I stood on that scale while I was at an angle, would I weigh the same amount? Would the scale read the same thing? What do you think? Would it change if I were standing on a ramp, standing at an angle? Think about that for a second. Well, I wasn't sure. And so I tested it out. I got my scale and I set it up on a ramp. I laid it up against the stairs and I did the same thing. And what I found was that I ended up weighing a lot less. Well, maybe not a lot. I ended up weighing a little bit less. I weighed 73.8 kilograms, which is about the same as 163 pounds. So by standing on a ramp, I ended up losing about 10 pounds. And that might seem a little weird to you. Why would being at an angle cause me to weigh less? Well, a free body diagram can help us to understand that because a free body diagram can show the forces, like gravity, that are acting on an object, like me. So let's walk through how to draw a free body diagram. First, you start off with a really simple object. It doesn't matter how good of an artist you are, you can simplify the objects by making them just simple boxes and circles in various shapes. So let's start with a box. It's pretty simple. That's me. You can then add a dot into the center of that object to show where its center of gravity is. The box is pretty even, so I'm assuming that it's somewhere in the middle. Then draw an arrow to show the direction of any force on that object. You can imagine gravity is pulling me down, so I drew an arrow pulling me down from that center of gravity. It's also good to label your arrows because we're going to have a number of arrows. So this one is the force of gravity, and I write it as a big F with the little words right next to it. You can then add other arrows to show any other force. And the thing about the arrows is that the size of the arrows matters. How long they are shows you how much force you think there is pushing or pulling on that object. So while gravity is pulling me down, the force of the earth, the ground underneath me, or the floor in my room, it was pushing me back up with that same amount of force, opposite but equal force. So the ground was pushing me back up, preventing me from falling, down to the center of the earth. And so I have the upward force matching the downward force of gravity. And that's it. That's all you have to do for a free body diagram. So let's go through this again. Now looking at what happened when I was standing on a ramp, standing at an angle. So again, I started with the box center of gravity, and gravity again is pulling me straight down. That's the force of gravity. It was the same size as before. But now the ground, since I'm standing at an angle, is pushing me up directly away from the ground at a slight angle as well. But now there's another force that's applying to me. Now there's a little bit of friction between me and the scale, or between the scale and the ground. They're all connected, right? But I'm just focused on the forces on me. So I didn't draw the scale. I didn't draw, well, I guess I drew the ground, but there's a little bit of friction pushing me back up. I might want to be sliding down the ramp, but there's enough friction to keep me in place. So that up friction arrow is much smaller than the friction of the ground, or the force of the ground, or the force of gravity, but it's going this other direction, holding me back up, preventing me from sliding down the ramp. And this little bit of an up arrow, it's pointing slightly up, that is what is reducing my weight. My weight, or the scale, read a little bit less because friction was holding on to some of that weight through the scale, and it wasn't reading on the scale itself. There's a little bit of a force pushing me back up that counteracted the force of gravity pulling me back down. So this brings us to an idea of balanced forces. When forces are pushing in opposite directions, they cancel each other out if they're, working on the same object. So in these diagrams, the force going down versus the force going up, 50 newtons going down, 50 newtons going up in the opposite direction, opposites, positive and negative, they will cancel out to be 0 newtons of force. We call this canceling out the net force. The net force is just the sum of opposing forces. So 30 newtons of force going in one direction versus 30 newtons of force going in the opposite direction. If you added those two up, since they're going in opposite directions, one's going to be positive and the other one's going to be negative, those will cancel out to 0 newtons of force. They're balanced. So it doesn't matter how much force there is, it could be 75 or 50. If they're in opposite directions, when you add them together, they cancel out. And this N that I've mentioned here, it stands for Newton. It's just the way we measure forces. It's a unit of measurement. Just like pounds or kilograms is how we measure how heavy you are, the mass. N for Newton is how much force there is, how much of a push or pull there is. But forces are not always balanced. So let's again look at the net force in this scenario. The up and the down net forces are balanced out. The net force of up and down cancels itself out. But these two individuals pushing on opposite sides, those are unbalanced. One person is pushing at 100 newtons of force going that direction, and the other person is pushing with only 50 newtons of force going in that direction. So 100 plus negative 50, opposite directions mean they're opposite signs. If you added 100 and negative 50, that would equal 50 newtons of force going this direction. And what would happen to this object if one person is pushing on it only a little bit and the other person is pushing on it twice as powerfully? Well, the object will accelerate. It will speed up. It'll start moving in that direction. If there is ever an unbalanced net force, then the objects will accelerate. That is a cause and effect relationship. Unbalanced forces cause objects to accelerate. Let's look at one more example. Think about this. Where are the forces when you're doing a push-up? Imagine yourself here. Again, we start off the same way. We draw a simplified version of you. We draw a dot in the middle for our center of gravity, and we start drawing the force. This is the force of gravity pulling you down. So far, so good, right? Well, in this case, there are actually two places that you're pushing up against the ground. So we have the force of gravity, and we have the force of your arms pushing you back up, right? You're pushing against the ground over here, pushing you back up. But if we stopped here, you can see that the force of gravity arrow is a lot bigger than the force on your arms pushing you back up. If we stopped here, gravity would win and it would pull you down to the ground and you'd be chest first onto the ground. But there's also a force over here at your feet. And this force on your feet is also pushing up. You're pushing against the ground, holding yourself up over here. So some of your weight is on your feet and some of your weight is on your arms. And if we added the weight of your feet plus the weight of your arms together, it would cancel out the force of gravity pulling down. Right? You might have 100 newtons of force on your feet pushing you up here, plus another 50 newtons of force pushing your arms or through your arms up over here. And that would cancel out the opposite force of gravity pulling you down over here. The net force would be 0. And if you wanted to actually then do the push-ups, you would relax your arms a little bit to make this number smaller, right? You'd go down. And then if you wanted to accelerate back up, your arms, you would have to push more than 50 newtons of force, and the combined force would be more than gravity, and you'd be able to push yourself back up. You go back and forth in order to increase and decrease the amount of force on your arms while you're doing the push-up. So how might you be able to make push-ups easier or more difficult? How could you increase or decrease the amount of force on your arms in order to make a really easy push-up or make a push-up that's really hard? What I'd like you to do, take some time, find a piece of paper. You can go to a digital drawing, whatever you need to do. And I want you to finish these two diagrams. Show the force on your arms and the force on your feet, and how would they be different in each of these two scenarios? Imagine doing a push-up on an incline here, where gravity is pulling you directly down this way, versus doing a push-up over here, going the opposite direction, where gravity is pulling you down this direction. Show the force on the arms and the feet in both of these to estimate which one would be harder, which one would require more force on your arms.